Hello everyone. My name is Nathan Cassereau and I'm with my colleagues Pierre Cornette and Hatim Bourfoune. And we are engineers at Idris for the AI support team. So the Idris is the institute, and we'll be talking about Jean Zay, which is the supercomputer. So at first I will talk about Jean Zay and Idris, and then later on Hatim and Pierre will talk about NLP more specifically. So Idris is a CNRS institute. It is the institute which hosts supercomputers for the research center. And the idea is to put resources in common for AI and high-performance computing researchers. So the supercomputer is owned by Jean Zay. Jean Zay is a national company, so it is owned by CNRS, INRIA, CEA, and so on and so forth. And it buys every supercomputers in France, any major supercomputer in France. And it also gives resources to researchers and teams. So if you want to have access to one of their supercomputers, you will go through their procedure to ask for resources. So basically, the story of Jean Zay started in 2018 when Cédric Villani, working for the president, decided that wrote a report saying that in France we were lacking research facilities for artificial intelligence and computing resources. So he basically said that we needed new supercomputers, and Jean Zay would be the best organization to purchase the machine, and it could be then hosted by Idris. And then in 2018, we started to publish calls for any company who would sell the supercomputers, and the idea would be to have a supercomputer which was both for HPC and AI. Before Jean Zay, supercomputers were mostly for HPC and not really for AI, but after the report it was decided that a good portion of the machine would be dedicated to artificial intelligence, because it would be a very important thing in 2020. And then a year later, Jean Zay was purchased. So Jean Zay is a Minister of Education a long time ago, and he created CNRS. That's why the supercomputer was named after him. So in France there are 3 major supercomputers. There are many more supercomputers which are smaller, but the 3 bigger ones are Jean Zay, Joliot-Curie for CEA, and Adastra for CNES in Montpellier. So Jean Zay was bought in 2019 and was the biggest one until Adastra was purchased. And since 2022, it is the largest supercomputer in France, but it is mostly dedicated to HPC and not as much for artificial intelligence. So for artificial intelligence, Jean Zay is still the most powerful. And so the compute power of Jean Zay comes from mostly its GPU. So for artificial intelligence and mainly NLP, you need a lot of GPUs, and we have a lot of them. So we have more than 3,000 GPUs, mostly V100 GPUs, but we also have 400 A100 GPUs with 80 gigabytes of memory. For the biggest model you may need to train for natural language processing. And it uses a bit more than 2 megawatts, but a small part of it is actually used to heat our building as well as the university. So we do, even though we uses 20 megawatt hour per year, we use 20% of it and the rest is wasted. But the fact that you can use supercomputers means that also the hardware is shared among users, so you will save a lot of money by using Jean Zay. Jean Zay is free for a research team. It was paid for by the government, so it is free for you as users. So Idris hosted many supercomputers before, and that's a bit of history of what Idris hosted, but some of the conclusion we can see the same conclusion in every compute centers. Basically, in 10 years, the electrical power was multiplied by roughly 10, but the compute power was multiplied by almost 300, so it is a lot more efficient than it used to be. And before Jean Zay, we had other machines, Blue Jeans, which were the most powerful machines Idris ever had, because it actually was in the top 10 of the global ranking of the supercomputers. So with Jean Zay, you have multiple partitions. So there is a CPU partitions for HPC, but it's not really your usage. But there are many GPUs, so V100 and A100. They are separated, so you can use a V100 and A100 at the same time. But you can choose which GPU you want to use, and all partitions have access always to storage, so you do not need to transfer your data set beforehand. So we have multiple partitions for storage. Mostly we have the work partition, which is a rotative disk, where you will store smaller dataset as well as code, but you also have a full flash partition without any quota for faster access. And if you need to use any of these resources, you just go through Slurm. So Slurm is a workload manager, one of the most common one in every supercomputer on Earth. And it is the one that we use at Idris. So basically, if we do not have this software, the issue that we have is that it is complicated to launch a job on multiple nodes. Oops. And also, we would have the case where every researcher would use GPU 0 and the other one would remain idle. So Slurm manages everything for us. And there is a fair share algorithm to ensure that everyone has a fair usage of the supercomputers. So to log in on Jean Zay is just a regular machine, so you can just go through SSH and then just launch your job, or you can go through Jupyter Hub, which is a portal to make it easier and more intuitive to use the supercomputers. So you can just do your Slurm submission with Jupyter Hub and ask for resources from there. And then when you will have your allocation, you can start notebooks. So you will have a more visual usage of the computer. So what are the services given by Idris? So we have courses, HPC as well as AI. We have also short-term and long-term support for research team which may require it, because some team may not have engineers. They may have only researchers and would need engineers to help them. And then we provide tools and environments such as Conda, Jupyter Hub, and also the DSDR. So DSDR is a storage space where we download a data set. So you do not need to download it, especially if there are terabytes of data. We do it and we put it in common, so we only do it once, which is very important, especially for computer vision, but also natural language processing. So that's the Idris team. So the parts that you may see is green columns, which is support team. So there is the HPC support team and the AI support team, which we belong to help you use the supercomputer. And there are also many other people which we do not see, but which actually make the machine work. So the mission of the support team is the help desk. So if you have an issue, you can send us an email, but we also answer the phone if you need it. We manage the software, so you do not have to compile it by yourself. We provide support and documentation, and then there is training, workshops, and hackathon if you need help. So those are the training courses that we offer currently. So there are many HPC courses, a few AI courses. So for instance, introduction to deep learning. So you're probably beyond that, but that's still a thing. And courses about optimized deep learning to make the most out of our resources. And one of our biggest one is the Fiddle one, which is free and online, which covers many themes in artificial intelligence. Finally, one thing that we have at IDRIS and many other centers is the PNRIA Engineers Network. So it's 20 engineers which are available as support for any team, any research team which would need it. Then you would just submit a project, and if you need an AI engineer, you would be allocated someone for like 3 months, and it would help you use your code on supercomputers and maybe do some development for you. So when you come to Jean Zay, there are many thematic committees which help allocate resources and give you hours. So the biggest one is the last one, artificial intelligence, because Jean Zay is now mainly an artificial intelligence supercomputers. But for HPC, there are basically every research field is represented. A few examples of things which run on Jean Zay. So there is AlphaFold. So AlphaFold is a famous code to do some prediction about molecules. So it was not trained on Jean Zay, but it is very often used for inference on Jean Zay, mainly by the Institut Pasteur. And there are a few networks which were trained and are somewhat famous. So there is DeepFawn, which is used by national parks to recognize animals. There is PlantNet also, which was trained on Jean Zay since the beginning, where you can take pictures of plants and it recognizes the kind. And there is the biggest one, so Big Science, which is it trains the model Bloom. So it is somewhat called by media as the French chatbot, although it is neither French nor a chatbot. And it was an international work with more than 1,000 researchers, but it was trained on Jean Zay for like 3 months. And it resulted in a large language model. So just to show you that it is possible on Jean Zay to train very large models, which you may need in your work. So what's the conclusion about all this Jean Zay project? So basically it was found that we have more than 1,000 projects, so it's working pretty well. So you may, so we may be trustworthy. And most of it is dynamic access AI for faster. If you want an access on Jean Zay, usually the AI community want it fast. So we introduced dynamic access to go much faster. And it's working so well that Jean Zay was extended actually 3 times, the last one with the 800 partitions, which added 8 petaflops. And when there was a survey, so it was found that 20% of AI researchers were using Jean Zay and 93% were satisfied. There is still work because 30% were not aware of the existence of Jean Zay, so there is still work to do to communicate about Jean Zay. So it is a quite a successful project to help researchers, so that's why we are talking about it, because you may need the resources of IDRIS. And yeah, so Jean Zay is successful. So it is it does make Jean Zay a bit more trustworthy for future supercomputers. So you may have heard that France has obtained from Europe funding for an exascale supercomputer. So it will be also purchased by Jean Zay. This time it will be hosted not by Idris and Sunrise, it will be hosted by CEA. Because only they have the electrical facilities to power such machine. But Jean Zay will keep living and will be updated with newer hardware to train a larger model much faster. So to get access to Jean Zay, it is quite easy. There is a website made by Jean Zay called idari.fr, and you can ask for you can submit a project and ask for GPU hours on this website. So depending on the amount of resources that you need, you will have two procedures. If it is below 50,000 GPU hours, it's considered as a small allocation, so it will go faster. It will be a dynamic access, and you will have your resources within a week. If it is more than that, you will go through a regular access, which is twice per year, and the allocation committees will review your project, but then you can ask for much more resources. Either way, you will go through, you will require an access because Jean Zay is a restricted area, so it is always possible to be denied. That's a thing to keep in mind, but most of the times people do obtain their authorization. And now Hatim and Pierre will talk about NLP more specifically.
Thanks, Nathan. Hello everyone. So just a quick reminder, if you have any questions, feel free to ask, as we have some time, so feel free. So for this part, we are going to present you the work we have done during the PLM for All project. So this is a project under the format of advanced support we had at Idris, and we were 4 engineers working with researchers to make the use of Jean Zay, especially for people using large models, easy. So, quick summary, we're gonna talk about data parallelism, accelerate, parameter efficient fine-tuning, and then Hatim will present you naive model parallelism and pipeline parallelism, and DSPs and Megatron. So, the first thing, I don't know if you are very familiar with this, I think you are quite familiar, but just a quick reminder. In the context of a supercomputer, we have different nodes. I took the example of 4 GPU per node, and in PyTorch, historically, so before we had the data parallel class to use multi-GPUs for one model. With the data parallel class, you had only one process, so the process is a MPI task. Usually on Jean Zay. So you had only one process that could use all the 4 GPUs to do a data parallelism on the model. But if your model is too large and does not fit on one GPU, you cannot use this class to do data parallelism. So we use a distributed data parallel class. So it is no recommended even if your model fits on one GPU, because it uses MPI backend and is faster to do the communications between the processes. And it works if your model does not fit on one GPU. And it also works in multi-node configurations. So that's all for the data parallelism. For the implementation on Jean Zay, we have a Python package, which is IDR Torch. So this package must be added in your code, And what it does basically, it defines the master ADDR and master port variables for your script. So you don't need to manually set them according to the nodes that has been allocated to you. And then it also recovers some variables that are useful for during your scripts and make them available for you in your Python code. So you can just ask for itertorch.rank or .size to have the world size and things like that. So to init your process, you have the torch.distributed package, and then we tell a user to use the Nickel backend because this is the one we have, and it is more efficient on Jean Zay. So this is a distributed sampler and data loader that you can initialize with the itertorch.size and .rank variables. Yes?
Just to mention that actually it's on Jean Zay that it can be used everywhere because the code source is online.
For this, I think yes. 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 So it is not very specifically for Jean Zay. It is for any cluster, and it recovers variables, environments, variables that are set by Slurm. So if you have another cluster who use Slurm, you can use the script that is also available online. And yes, also all the work I am presenting to you is also publicly available on the PLM for All Git, which you can see a link here. So it is, I think, available for all the Slurm cluster.
The script that we provide on that Git, it's made for Jean Zay. Basically, but I think you can easily adapt it to your cluster.
Okay, thanks, Hatim. Okay, so another thing we worked on is how to use the Hugging Face library Accelerate on Jean Zay. We had quite a struggle for the implementation because we didn't understand that we need a config file for each node in the process. So we made a script that creates those files, and here it is. So it is available on the PLM Git, and then to launch your script, you just need to run batch accelerate launch with the config file that you set accordingly. So as you can see here, we took a very basic configuration. So for now, you would need to edit this file if you want to add, for example, the diff speed config in your script. So this is a work in progress, and we haven't tested every accelerate features now. So it is we are going to test it during the few months. And so there is also a Megatron LM config and a FSDP config. Now on your script, what does accelerate do is but it's only a wrapper that you put your model, optimizer, data loader, and scheduler in. And then it handles for you all the data placement, for example, so you don't need to take care of the model to GPU. So it does it for you, and they know whether your model is, where your data is, and where your data need to be. Only for classical training. If you have data that needs to be on a particular GPU, you need to set it yourself. So it replaces all the distributed data parallel lines of code that we saw before also. Then there is another Hugging Face library we worked on. This is a PEFT library. So PEFT stands for Parameter Efficient Fine Tuning. It is mainly used for LLMs nowadays. And we also, we created a module on Jean Zay. So this is not available on all clusters for this module. This is just a Conda environment where we put all the Python package useful for training LLMs, and we update them very regularly, so they are always up to date. And so if you want to test new features, it's the module you need. And then on the PEFT library, there is a huge programming effort made by Hugging Face for now. And they already implemented LoRa and QLoRa that are adapter techniques, and the paper is very recent. And for example, they are the only one who implemented them in the library for now. So if you want to use it with another library, we need to rewrite the code from the paper. So that's something they did. And they also work with their other library with Accelerate. So it is compatible with DSpeed and fully shared data parallelism. And they are also implemented other parameter efficient fine-tuning techniques that are prompt tuning, perfect tuning, p-tuning, and EA3. So now I will let Hatim speak to you.
So before I start my part, as Pierre said, PLM for rows, it's in work in progress. So if you have a suggestion about tools that we didn't present, you can tell us, because at the end of PLM for all, what we want to do, it's a huge benchmark of every tool, and we show on Jean Zay which tools are the best to fine-tune model, or even for inference for model. So if you have suggestion about tools, just you can tell us at the end. So now my part, I'll start with model parallelism. So as you know, when the model is too big to fit in one device, like for example Bloom, you need to do what we call model parallelism. So you have to know that with PEFT, with QLoRa, so which quantize 2 times a model, even Bloom can fit in one device. So I think Llama can fit in one device, but even with a double quantization, you can't fit Bloom on one device, so you still need model parallelism. So the first technique I'll show, it's the naive model parallelism. So it's the simplest way to do it. You just slice your model in different parts. You put different parts in your different device, and then you compute sequentially the forward and the backward of your training. So as you can see, it's very inefficient, because like the whole white space that we have, it's a GPU waiting, and as you can know, GPU compute, it's very expensive, so it's the kind of thing that we don't want to do. But in case you want to do it anyway, there is a very easy way to do it. So first with PyTorch, when you instantiate, when you create your model, you just have to put your different parts of your model into different device, and in your forward, you just pass the result of one device to the other one. With Accelerate, it's even simpler. You just have, when you do your front pre-train, you just have to add device map, and then the way you want to be your model to be sliced. So, for example, there is automatically, and then Accelerate will automatically put different part of your model into different device. But it's still very inefficient. It's very slow, so you should use it, like for example if you just want to try a model quickly. But if you want to do fine-tuning or other things, like I really don't advise you to use this. So there is an even better way to do model parallelism, which is pipeline parallelism. The best, the first method, it's what we call gpipe. Basically, you kind of do the naive parallelism, but with gradient accumulation in a smarter way. So you slice your batch into different parts, and you sequentially compute your forward and backward loop as always. So there is a way to do it with PyTorch with the RPC module, so that I put here. It's how can I say? It's still a bit easy to use it. The only problem is first you have to use it within one node, so it's not working on different nodes. And also you have to initialize the RPC backend correctly. For example, on Jean Zay, we had to find that it's those options that we have to use and not the default one. Then how you do it, you just make a list of your different layers, or even in a sequential module, and then you pass it to the pipe module of PyTorch, and then you have your model with pipeline. A more optimized way to do it, it's with pipe dream flush, which is the default pipeline parallelism used by DeepSpeed. So I'll talk a bit about DeepSpeed. So as you can see, the bubble it's even smaller, so it's even more optimized. So I'll talk a bit about DeepSpeed and how you initialize it on Jean Zay. So normally, if you use DeepSpeed before, you should have used the DeepSpeed launcher. But on Jean Zay, I think it's more practical to directly use what we call the MPI search environment. So basically, you use the command srun to execute several times your Python code. And then when you initialize your distribution with DeepSpeed, you just put, well, the NCCL backend, because we're on Jean Zay and it's best on Jean Zay. And then the init method with env. And basically, it will automatically find every GPU that you'll use for that training. So it will, if you do pipeline parallelism, it will directly slice your model into the right device. So it's what we advise. Do not use the DeepSpeed launcher, but use the srun. But of course, you can still use the DeepSpeed launcher. It's not. You can still use it on Jean Zay. So after you initialize DeepSpeed, there's several ways actually to do pipeline parallelism. Here I show the way with the pipeline module of DeepSpeed. So basically you create a class, and then in that initialization of that class, you initialize, you cut your model on different parts. And then, we'll see just after how we instantiate that model. But you just have to have like a list of the different layers that you can slice. So basically, if you use a transformer model, usually the first layer will be the embedding, then you'll have all the transformer layer, and then maybe at the end you have a linear layer. So you can put all that on the list and give it to the list. Just a little tip too, you can use what we call smart loading when you use the pipeline parallelism. It's because if you don't use the smart loading, because we execute several times the code, if you load, for example, a big model Bloom on a GPU, it will load 8 times the model on the CPU RAM. So a way to pass that is to use what we call layer spec, and basically you just wrap your part of the model on the layer spec to basically do what we call smart loading. After we do that, so you can instantiate your model with all the different parameters that you're going to use. Also, you can use which partition method you want to use. Basically, here I choose uniform. It means like it will treat each layer of the model like the same. It will not be, for example, a smart way to do it with Bloom, because the embedding layer is way bigger than the transformer layer, so it will take more space. But it's just to show it. So yes, and then you put your model on deep speed initialize to get your model engine, and basically with deep speed, it's how you do the forward and backward. It's with that model engine, and of course you give the deep speed configuration. Also, another way to manage your GPU memory in a smarter way is to use what we call deep speed 0. Deep speed 0, there's several stages of deep speed 0. The first stage will simply slice the states of the optimizer. So it's very useful, for example, if you use Hatim optimizer, because the Hatim optimizer, there's way more weight than the gradient and the weight of the model. The second stage will slice also the gradient, and the last stage, the stage 3, will slice even the weight of the model. And so each device will have just one part of the model, of the weight, and of the model, of the gradient, and the optimizer. So to do it in Jean Zay, it's pretty easy actually when you know how to initialize deep speed. You just write your config. So as you can see, I put like basic config with microbyte size, Hatim, etc. I use BFSS because it's better on A100. And then I choose the stage that I want to use. So 1, 2, or 3. Then I initialize, of course, deep speed like I used to do. And there's a tip here to do smart loading when you use a Hugging Face model, is to simply call the training arguments class of Hugging Face. Then it will use the smart loading that I talked before. And what Hugging Face do actually, they use the deep speed 0 init context to do the smart loading. So then you call your model like always, and then you just pass in the deep speed initialize function the model that you just load. And to finish, I'll talk a bit about Megatron. So Megatron, the major advance that the best quality of Megatron, I think it's what they call the tensor parallelism. Basically, you not slice your model into how can I say, part vertically, but it depends on how you see the model. Let's say like you not slice the model at between layers, but actually you'll cut the layer into different matrices. So as you can see, what the tensor parallelism do, they just cut the different matrices and do twice. For example, if it's 2 devices, you'll do twice the compute on each device. Then you put in common a first time here, here your result, and then you'll pass to the next part and do the same. So as you can see, there's 2 all reduce operation. And because of that, tensor parallelism is better when you use it within a node, because on Jean Zay I'm talking, because within a node we have what we call the NV links, which is a very efficient link between GPUs. But when you are between nodes, pipeline parallelism become more optimized because there is less compute between devices. Yeah, it's better when we have NVLink, but between nodes it's kind of hard. So how to use Megatron is kind of easy actually when you know how to instantiate it. So basically you just choose your Slurm parameter, and then you use the srun to execute your Megatron several times. So for example, here I tried it on a fine-tuning task, and I just use a factor of 8 for tensor parallelism and 2 of pipeline model parallelism. Why? Simply because I have a GPU within a node, so I'll do tensor parallelism within the node with that. And I have 2 nodes, so I want to do pipeline parallelism between the 2 nodes, so I do that. And then I also use that backend because it's the best on Jean Zay. And a last way to do tensor parallelism is to use deep speed inference, which is, I think, it's the best, it's the more optimized way to do inference on big NLP model. So you initialize the deep speed like we saw it before. You can call the model in a smart way or not, like we saw it before, and then we just call that class. We change the attribute of word size. Here you can use IDR torch word size to know the number of GPU. And then you pass your configuration into the init inference, and you can do your inference like you will do it. And that way, so we tried, and it's this one who is the more optimized on Jean Zay for inference. Little summary of which tool can do what. So as you can see, every tool you can do a DDP with it. You can do pipeline parallelism with PyTorch, but only on one node. On Accelerate, so as you can see, it's still work in progress, so we didn't try a lot of things. And for example, on Accelerate, they said that we can use Deep Speed 0 and Megatron PP and TP. But we didn't try it yet, and we didn't see actually a lot of code on it, so actually we're curious. If you used PP, TP, and 0 on with Accelerate, if you can tell us at the end, we'll be interested. Then pipeline parallelism, as you can see, we can use it on deep speed, but it's kind of hard to implement it. So we suggest to pass into Megatron if you want to use that. Tensor parallelism, if you use inference, no-brainer, it's to use deep speed, but for training, maybe, Megatron is the best, I think. And also something that we didn't talk about, there is a version of Megatron which is deep speed Megatron, and you can use TP, DDP, PP, TP, and 0 stage 1. Actually, it's with all that configuration that Bloom was trained on Jean Zay, and the big science team told us that, it's the most optimized way to do it on Jean Zay. Also something that we didn't talk about, it's the PEFT technique that Pierre showed are compatible with some techniques that we show. For example, you can use the 0 stage 1 and 2 with QLoRa. So for example, if your model is too big or for training, but it should be very big, or even if you want to do data parallelism with QLoRa, if it's still too slow to use QLoRa. So yes, and that's it. And at the end, so we hope that we'll have a benchmark of every method with every tool. That way you can know which way it's the most optimized way to do it on Jean Zay. And that's it. Thank you.
Any question? So I will start with one because Jean Zay is obviously a French HPC, and it's easy for French to use. We know that in the room we have some people from outside France who are using it. But we also can use other European clusters, like I know there's one in Sweden that we can use. But are there good ways to collaborate? What's the network actually of HPC centers in Europe or in the world? Because as researchers, you have people from many countries, and it's so easy when you can share the facilities to collaborate, like data, models, and everything. So how can we do to collaborate like this?
Currently, there is no real network worldwide. We are trying, but it's still a lot of work to do to do something, but it would be within France. So basically, one idea would be to share datasets between Jean Zay and Ad Astra and the future exascale supercomputer Jules Verne. But mostly it's still very difficult, and such structure, I don't think there is any advanced structure which would do that.
Okay.
So maybe I'm asking the same follow-up question. I'm kind of wondering how many people in the room could benefit from this talk. I mean, it seems like, I gather this is unavailable to most of us. Is that right? No?
It's not unavailable to most of you. Actually, the idea of Jean Zay is that it is available to all of you. So you would need to ask for resources on Jean Zay, but then Jean Zay is open and it's free, and then you would be able to use everything that we installed on Jean Zay.
Yes, and so there is something that the government is investing in Jean Zay, and one of the points that you need to have to access Jean Zay is that your laboratory needs to have the French government in one of the the one giving money. So that's one of the parts that.
Right. So in other words, it's unavailable. I mean, right?
So which part actually, like Jean Zay or Pierre
I don't have a grant from the French government, right?
Yeah, but you know that last part, PLM for all, it's available for everyone. So we provide easy script to do all the techniques that we show, and it's a public GitLab, so you can use it. And the benchmark will be on Jean Zay, obviously, so you know which one is the best on Jean Zay. But you can take into account which compute that we have on Jean Zay, and then I don't know, like it will be a first hint on which one will be best on your cluster.
Yeah, and maybe additionally, to be on Jean Zay, actually, you need to have, I think need to have French partners. But if I'm correct, for the Bloom project, there were how many countries involved? You said it before, and there was no general funding, like one agency funding everybody. So it was really a collaborative project. Correct me if I'm wrong, but collaborative project in which institutions from all over the world benefited from the infrastructure. So like there was Hugging Face, there were universities from US, for instance, involved in the project. And so that's one way to collaborate. Of course, you have restrictions regarding the security, and some people in the room know that. But I think that's a good way to collaborate also, so that's why we are pushing to get the infrastructure available for international projects. Actually. Any question regarding the availability maybe, or the techniques used, or politic questions?
Maybe one question that might be on the minds of people who are not in French institutions, like either US or other European countries or even Malaysia. What is a model for partnering with someone in this way? In other words, how are these consortia formed? So let's say I'm not thinking about what to do in the next 2 weeks for JSALT. I'm thinking in the next 3 months, can I write some application so that for the follow-on work that I want to do from JSALT, I can use these resources. So is there an existing successful model or some partnership, or do you want to say how one might build one? This might not be a question for you, I don't know. Maybe it is for you, but imagine that I'm at Johns Hopkins in the US, right? And I would like to do some experiments which might require this kind of computing. So what is my path? What's an example saying, look, this other person from Boston University did X, so do something similar. Find a French university partner, I don't know, can you point me to something and say this is how you use it? So that's what I think Ken is saying. He doesn't see how he, as a researcher in Northeastern University in the US, can use this computing. So I think the answer he's looking for is, here is the recipe, here is the model, here's a past partnership where somebody in America was able to use Jean Zay.
Yeah, on our side, what we can say is, if you have a French partner, you can ask for that kind of compute. You go to this website that we show, you explain your project, and you can have it.
Okay. Yes, so that is true. So it is a French national investment, and okay.
Yeah, you need French partner, that's true.
Yeah, so actually, I thought there was a European policy to develop some European computation center so that we can access. I know as a French researcher we can access supercomputer in other countries, and without any partnership. But definitely in France, if you want to access this, you need to have you just collaborate. There's no need to have a funding like a NSF binational project, for instance. You just have a research project that you describe. You make a proposal for 2-4 pages, and then you get the facilities to compute. And the good thing is you can really have multiple nationalities involved.
Evidence is that, I'm assuming the evidence is that there are non-French people using this at JSALT. So, QED.
Yeah. So again, there are some restrictions about security, but yes, definitely it's possible. And
about the access from foreign people, I just have a question, and maybe just some people of our group are wondering why some nationalities are banned from Jean Zay, like Argentina, for instance, to cite only them. Even if they are involved in the European project and in the JSALT project. So I don't know if it's not your domain, I think, but if you have any clue, it would help maybe.
Yeah, officially there's no nationality ban from Jean Zay. Officially, I said. But you want to...
Yeah, there are no nationalities which are banned. We have also Chinese researchers on Jean Zay. But the French government gave itself the right to deny any application, and they do not provide any kind of justification. That's the policy, no justification ever. So if someone is refused, so I don't know about Argentina, maybe there was another reason, but we cannot know, and they will not answer this kind of question. They refuse.
I also would like to share an experience. I don't know others, but I submit a few times, and every time if you tell me I miss a document, and then I resubmit, and then you tell me I miss another document. So I end up I give up. Okay, maybe this can be can be managed a bit better.
Yeah, there is a new procedure that is being created, so it is more streamlined and straightforward. So it will no longer be a SAV, but another software to help with this kind of procedure. But
yes, they also recently updated the diary website so that every person who asks for resources can know the state of the project, and if something is missing, he can see on the diary website. So that was the point many users told about what's the problem, a non-problem, and now it's the tentative to solve it by giving more information to people who want to access, so where the state of the application is.
Any other question? Yeah, Santosh.
So, you think Jean Zay will be part of Euro HPC in the future?
Euro HPC is for the new exascale supercomputer Jules Verne. I don't think Jean Zay will be part of it.
Thanks.
We heard the word supercomputer a bunch, but I don't really know what that means. Back in the day, Cray computers were building these things that were extremely expensive and really quite leading edge. But they actually never built very many of them. And I used to say I wouldn't use a computer I could afford, but at some point, you know, my wife came home with a computer we could afford, and it was really better than the computer I'd used 10 years earlier. And Bob Mercer, in his Lifetime Achievement Award talk at ACL, compared a Cray back in the day to the cell phone he had at that time. And the Cray was heavier, but in fact the Cray was not competitive in any way with the cell phone. And I think the lesson to come here, there was a friend of mine who was starting a supercomputer business back in the 70s and 80s, and he thought that he was competing with Cray, but he actually got beaten by PCs. That PCs were, he thought there were diseconomies of scale. The computing was cheaper, faster, better in smaller computers than bigger computers. And my economist friends told me that he didn't understand economies of scale. Economies of scale are not about the size of the computer, they're about the size of the market. So if you're building a one-of computer, it's not going to be competitive. And so what I'm wondering is here, is this basically just a cluster? Is it just, is it just using commodity parts, very reasonable? Or is it doing like what Cray's doing these days, which is building a one-of, biggest, baddest thing that will not be competitive for very long?
Yes, so usually the supercomputers that are built have a lifetime of around 5 to 6 years. So they are usually at the top in terms of performances when they are installed, and then they decrease with the time because the computers are always more and more powerful. So the main usage of supercomputers is that there are some things that you can do on supercomputers that you can do on your PC. For example, training a very big model, you need many nodes with a very strong interconnection between the nodes to exchange data. So that's something you have only on supercomputers.
Actually, the difference between supercomputer and like maybe data center, like cluster, classical, it's the connection between the different devices. It's that we pay the most, and that's why we consider that a supercomputer, and like another thing, a data center. It's the connection between the device.
So you didn't describe that. I mean, how fast was the internet?
I think within a node you are at something like 600 gigabytes between GPUs because of the NVLink communications.
Right.
It is a bit slower when you're leaving the node because you're not using NVLink, but you're using OmniPath network, which is a bit slower, although it is more flexible.
Yeah, but NVLink is limited to a very small number of GPUs, right? I can't use, I mean, they don't connect. You're not going to get thousands of GPUs connected that way, are you?
No, it's limited to a node. That's why tensor parallelism.
Yeah, I understand. A node is like a tiny number of GPUs, right?
It's usually 8, yeah.
Yeah. So within 8, all right, you get that speed, right? Okay, fine.
That's
but
why
we normally consider that to be just one machine.
Well, the idea is that still the OmniPath network is much faster than we would have on any data center. That's why it's considered as one big computer rather than 1,000 on smaller one. And the fact that NVLink is much faster, that's why we take it into account when we're doing parallelism. The paradigm changes depending on the number of GPU and the configuration we have. That's why we use tensor parallelism within the node because it's communication heavy, and then pipeline parallelism across nodes. So there are differences, but it's still much faster than consumer-grade computers.
So just before, actually, I understand that for non-French people, it seems very far and maybe not very useful actually to know the French facilities. But when discussing with different partners, it's very difficult, I think, to know what kind of infrastructure is available if you want to collaborate with other countries, other partners. What exists in other countries. I mean, even in France, I'm not sure I know everything about the facilities we have. And I thought that there's really some kind of value here to exchange on these topics, because I think there are good practices, there are ideas there. In the framework of JSALT workshop, when we are talking about collaboration, I think everybody's struggling in the groups. I mean, Ken, you're the first because you were asking for USB sticks with 5 terabytes at some point. And
Actually, I found that the network is better in my apartment than in this building.
Really?
Yes. It's not only faster, but it's also got fewer security blocks.
Yeah, definitely, yes.
The security blocks here are mind numbing, to the point where I actually do all the transfers in my apartment. Anyway, yeah. So we could certainly discuss, but I mean, I had a Slurm cluster in my university. Also had one at Baidu.
Mm-hmm.
The stuff that's being described here, we all had that at Baidu for sure. Lots of GPUs, nice network within the pod, right? But one of the things that I have at Northeastern that I never had at Baidu is lots of disk space and lots of RAM. Maybe not so many GPUs, but disk space and RAM are cheap and really valuable. GPUs are expensive, and I'm not so impressed. Right? They're not that much faster than CPUs, and I'd rather have 1,000 CPUs than 10 GPUs. I mean, than 10 CPUs. That's you can work it out what the numbers are. But being able to allocate an array with terabytes is really very, very useful. So I'm worried this is sort of, and one of the thinking we had back in the day, Slurm is kind of how people would do things 5 years ago. But these days, I think people are moving more towards AWS kind of model. I worry this is not that leading edge. So it'd be interesting to really do a comparison.
Okay, I'll let this for the discussions after. If there's no other question?
Just about that, there's a big difference is that Jean Zay is free, totally free for researcher. Oh, no, it's available for some people. It doesn't mean that, but it's free for the people who are available.
I mean, if you're at Northeastern, our network's free too.
Oh, yeah, maybe. I didn't say that.